Greetings and welcome to a new video. In this video we will discuss the low-pass filters in great detail. We will discuss how we can calculate the transfer function, the cutoff frequency, and what the effect is of cascading the low-pass filters. Of course, we will see that step by step in our calculations and verify these in SPI simulations. Now, before we dive in our examples, let's first discuss the filter sharpness. If you have a low-pass filter characteristic, which is the Bode plot like so, this is a one single pole RC low-pass filter characteristics. You see here the first region, which is the passband region. It's also called the bandwidth. It's up to the FC, which is our cutoff frequency. And this region where you have the transition, which is then going in the stopband region, has a slope of minus 20 dB per decade. Now, you also know that the cutoff frequency is then minus 3 dB point or 3 dB lower than the low frequency gain. But how can we make this slope steeper? So going down faster. So we can increase the filter sharpness and make it more ideal by increasing the filter order. And now by increasing the filter order, we need to add more components, so more complexity. That can be done by cascading first order filters. That can be done in passive or active form. You can use multiple feedback circuits or more advanced active fill circuits. We can keep the cutoff frequency the same for single stage filters. That is actually what we want. So how do we do that? That is actually also one of the important questions. So actually what we want is we need to keep this FC, which is our cutoff frequency, the same, but we like to go faster down like this. So not minus 20 dB per decade, but minus 40 dB per decade, or maybe minus 60 dB per decade. So this is a first order, second order, and a third order. So if you go to the fourth order, you will have minus 80 dB per decade. So for each order, you will add minus 20 dB per decade. So that is a very important question. So how do we do this operation? Now let's also first look at the characteristics of a very simple prototype first order RC low pass filter in the passive form. This is the circuit we know. Now we have the resistor and the capacitor in a very simple form. This is the low pass filter most often used if the circuit needs to be very cheap and fast and easy to use. So we have here our circuit, and now we can determine here the transfer function in order to see what the cutoff frequency is and also the phase. So for the transfer function, we'll use the Laplace transform. So we have here the H of S, which is then the output voltage divided by the complete thing of the input voltage. So that is also done using the voltage divider rule. So the 1 over SC, which is the expression in the Laplace domain for the reactance of the capacitor, divided by the series combination of the R and the 1 over SC. Now we can now multiply the numerator and denominator by SC, then you have this expression. Now when you go to the J omega domain, so in the steady state analysis, we can replace the S by J omega, then you have from here this expression. Now when you move on, you would like to calculate the magnitude and the phase. You can look at the absolute value of this expression, which is a complex expression. So you can say 1 over the square root of the 1 squared plus the omega RC, the quantity squared. That's actually shown here. Now the 1 is of course just 1 squared is of course just 1. Now you have this expression. You can also convert that in dBs, which is most often used in the Bode plots. Then you need to take the 20 log of what you have here. So that's actually expressed here. How about the phase? Now the phase is given by theta. That is for this situation the phase contribution of the numerator minus the phase contribution of the denominator. And in this case, the contribution of the phase for the numerator is 0. So that's why I have you here 0 minus the arctangent of the imaginary part divided by the real part. That's actually shown here in a simple form that's actually given here. So the phase is dependent on the omega, the resistor R, and the capacitor C. Okay, so the Bode plot for this situation, in ideal case, you have this red line. You see here it is flat, going up to the cutoff frequency, and then going down with a slope of minus 20 dB per decade. The actual response, or the actual curve, which is given in blue here, is going down a little bit faster first, and then approaches here at the cutoff frequency, which is then minus 3 dB point, or 3 dB lower than the low frequency gain, and it has this slope for higher frequencies, which is then minus 20 dB per decade. This is the gain, again expressed in the dBs, which is given here as 20 log of this transfer function in the magnitude form. The phase of this situation is starting from the 0 degrees and then approaching this minus 45 degrees at that cutoff frequency. That is the characteristic of a first order RC low pass filter, and is approaching for higher frequencies this minus 90 degrees. Okay. Now how about the low frequency gain? Now we already said that the low frequency gain is here 0 dB, which is 1 as a scalar value, so we can also look at it in the transfer function in the magnitude domain. So if you substitute here 0, you will get 1 over the square root of 1 plus 0 squared, which is indeed 1. Now if you take now the 20 log of that value, which is then expressed in dB, which results in 0 dB, so as we have it in the Bode plot here. What about the cutoff frequency? The cutoff frequency is given here by this formula, which is then also a unit of radians per second, or if you want to have it in hertz, you divide this expression by 2 pi and you have now 1 over 2 pi RC. Now in order to calculate the cutoff frequency, you can substitute the expression which you have here and equate that to 1 over the square root of 2. That is the definition of the cutoff frequency. But if I now substitute this cutoff frequency expression in here, which is then here 1 over RC, this will be 1 over RC times RC will be 1. So that will then result in 1 over the square root of 2. That is actually the expression again for the cutoff frequency. Again, if you now look at the dB scale, so you can then convert this to the dB units in 20 log of that, it's approximately minus 3 dB here. Okay. Let's now look at a situation where you cascade two of these first order low pass filters. So we have this low pass filter again, RC, and we do right after that this RC filter again. What do we get? Now the situation is now a little bit more complicated because now you have two RC circuits and this will be a second order filter. So how do we work out now the transfer function for this situation? Well, let's start with the noting here the nodes A and B, and then use a node voltage method to go from the input VA into the output. So I call this the I1, which is my current, and here I2, which is this current, I3, so I designate here also the plus and the minus for the current directions, and I4 here. Of course, the I3 and I4 are the same, but we'll need that later in our analysis. Let's first start with the KCL, which is the Kirchhoff's current law at node A. That means I1 is equal to I2 plus I3. What is I1? Everything is of course in the frequency domain here, so that means Vin minus VA over the resistor, that's actually shown here, this is this current, and then we have this current, which is then the VA, this voltage, divided by the reactance of this capacitor, which is then 1 over the SC, and we have also this VA minus VB, which is also the V out, so we can also write it down like so, VA minus V out over the resistor R. In this case we have the same resistor, so R and C and C. It can be also the case that you have different resistors and different capacitors. Then the calculations are a little bit more complicated. So we can now work this part, the first part of the right side. You can say now you divide actually by a fraction, so you can multiply that numerator by SC, and you have this expression. The next step, I will now multiply the left and the right hand side by R, and that's actually what you have here. Now I can now collect the terms with the VAs here on the right side, and I can move this minus V out to the left side, and I have this expression. So you see here 2 times VA to the right side, and I have also this term, so everything is here now in the parentheses. Let's call this equation number 1. Now going to the node B, which is the next equation we will use, that is then I3 is equal to I4. We know what I3 is, which is then VA minus V out over the resistor, is equal to V out over this reactance of this capacitor, which is the exact same as this capacitor, so 1 over SC. Again, we proceed as we have done before, so we have done this expression, so you just do 1 over the fraction is this multiplication here with the V out, and you now also multiply the left and right hand side by this resistor R, and now you can also take this V out to the right side, and you have now this expression for VA, which is then given by this expression. Now if we now note this as equation number 2, we can do the following next step. Substitute now this equation number 2 in this equation number 1. Why do we do that? Because we like to have an expression where you have the V out and the V in and also the components only, not the VA or other parameters. So that will allow us to write down V in plus V out is equal to this expression, which is actually this expression times the VA, which is from here. That's actually shown here. Now when I now work out the parentheses here, so I leave the left side as it is, I just work out the parentheses here, so SRC times SRC, which is then S squared R squared C squared, and I also do SRC times 1, and also plus 2 times SRC, so that will be then 3 times SRC, and the final one is 2 times 1. Then I have this expression. Now I would like to have here an expression where you only have the V outs, but I also have here V out, so let me then also subtract this V out from the left side. Then I also have, of course, here 2 that will then change in 1, so I know that I have 1 less. Now I have an expression where you see the resistors, capacitors, and the parameter of Laplace S, and also the V in and V out. So this is exactly what I wanted. Now I want to set it in the transfer function form, so now the transfer function can be written like the V out over V in, which is our ratio. And that I called now here G. So I call G, which is then V out over V in, and that will be then 1 over the expression which you see here. You can also check that by cross multiplication, and you will end up to this this equation. Now if now again substitute the S by J omega going to the steady state analysis, then you will have this one where you see here the S squared is J omega quantity squared. That means then minus omega squared you've changed. So here, so that will be the real value. So this will be also 1. That will be then in front. So 1 minus the omega squared R squared C squared plus, and you have here now J omega. I put it in front, and now we have 3 times RC. Now this is an expression we can use. This is the transfer function in order to calculate the gain, phase, and also the cutoff frequency. Okay. Now let's also look at now the situation for the cutoff frequency. So the cutoff frequency for this circuit where you have this transfer function can be calculated using again the definition, because we know the absolute value of this G for this circuit, the transfer function. If we equate that to 1 over square root of 2, we can go to the omega we want, so which is the omega cutoff. So this is now the expression for the gain. And where you see here the gain, here again we do the following: 1 over the square root of the real component squared plus the imaginary component squared, actually, which you see here. So if I now equate that expression to 1 over the square root of 2, that's shown here, and then I can see that I can equate the denominator equal to that denominator here, which is then actually shown here. I can now square the left and the right hand side, so I have now this expression, and now work out the parentheses here of the square here and also the square there. So I have now this expression, and I see here now the R to the power 4, C to the power 4, and also omega to the power 4. And this one and that one will end up to 7R squared, C squared, omega squared. And I have also here this 2, which is then replaced with the left side will be then minus 1. Now this expression we need to solve in order to look at the expression for the omega, which makes this true. We can set now here the x is equal to omega squared. Why? Because we have now a fourth order equation, which is now a little bit difficult, so we can replace that and make it now a quadratic equation. You see that actually by doing x is equal to omega squared, we will have an x squared here, and you will have an x here. That's actually the replacement here for the omega to the power 4 and omega squared. Now we can now use this formula, so we can say solving using this general expression we know from quadratic equations, we can say the b is actually this one, the a here, what you also need is this in front of this x squared, and the c is here, this minus 1. So we can say the solutions for x is then given by this. So you'd actually take the b here, you place it here, of course with the minus sign in front, and you do now the square root of b squared minus 4ac. Now you do 4ac, and a is this one and c is minus 1, so you will get a plus 4 here, and you divide by 2 times the a, which is then this. Okay, now you will see that this will be then 49, because 7 squared is 49, and then r squared squared is r to the power 4, and c squared squared will be then c to the power 4. And all this together will be then 53 r to the power 4, c to the power 4 in that square root. You can now take this r to the power 4, c to the power 4 out of that square root and make it actually like so. So that will be then r squared and c squared, and then you have only that square root of 53. Now we can now divide out the r squared and c squared from the numerator and denominator, and that will be then like so. So we will have only -7 here, and here plus or minus the square root of 53, and here of course here now only r squared and c squared, also that's 2. Now we will recognize here the following things, because I can write this as shown here. So we can have this factor, so this scaling here, and I saw here also 1 over the r squared c squared. Now if I now want to go to my omega, I will first look at the first order low pass filter. This low pass filter I see here, I know that the cutoff frequency was given by this, so I just call it now omega c1, just to emphasize this is the first order low pass filter. So if I now go to the omega, which is the square root of x, which is this, so I will take the square root of this one, which is now this big equation. I can now make the square root of this expression, which is just a number, times the square root of that one, which is also written like so. But this is here the omega c1, which is the cutoff frequency of this first order low pass filter. So I can also write it down like so. And this value, which is of course not easy to determine maybe, but this is the value we need to multiply our cutoff frequency of our simple first order low pass filter to go to the cutoff frequency of this second order cascaded low pass filter. So in this case we can say omega c2, which is then the second order filter cutoff frequency, is this much the cutoff frequency of the first order low pass filter now, which is approximately here 0.3742, and then that means the cutoff frequency you have calculated for your simple first order low pass filter will be approximately 37.4% times the in this case 37.4%. So that will be then much smaller in this two-stage low pass filter. Now, when you do a different configuration, which is then buffered, so we actually have the same circuit, only this unity gain feedback op-amp circuit here. So this is a voltage follower or a buffer. What happens in this case? Now, this is a more simple circuit. Now we can isolate the left and the right RC circuit, and our transfer function is like so. I call it B for buffered. Again, V out over V in. I see now here 1 over 1 plus SRC, which is then the transfer function of the first part, times the, again, the same thing. So because we cascade, we can multiply that easily. And since that is isolated, I can do that here. And it is also written like so. So we can square the denominators, and you have actually here, and it's of course 1 times 1, but it's effectively again 1. I can also work out the parentheses here, so you can actually here see what happens. So this is just working out the parentheses in the standard form. Now going to, again, S is equal to j omega, I have again this 1 minus omega squared r squared c squared, standard discussion as we have done before, and now we again j omega 2rc. Now let's also look at the cutoff frequency of this one. Again, the definition as said before, so we take the magnitude, we equate that 1 over the square root of 2. That is the definition for the cutoff frequency. Now, this is the magnitude expression for our transfer function B, and I will now equate that to 1 over the square root of 2. Now, we know again, this denominator must be equal to the right side denominator. Again, the same expression. Now, we have now here taken the square root of the left and the right hand side. Now, again, work out the parentheses and also here. So you will have now this again, exact same procedure as we have done it before, then for the cascade of the two first order low pass filters. And now we have this expression, and what you see here is again we can set x is equal to omega squared to move on and calculate the cutoff frequency. Similar discussion. So we can again do this and solving that using the formula for the quadratic equations, and we end up here, and now you see here this 4, because this 2 squared is 4, and you will now end up to 8 here in total. And again we take out here the r to the power 4, c to the power 4 as r squared and c squared, and then now the And the next step will be then divide out the r squared c squared from the numerator and denominator as said. And now we have this minus 2 plus or minus the square root of 8 divided by this 2r squared c squared. And again, we can only use the positive value of the x because the omega squared need to produce a positive value. That means we can only use minus 2 plus the square root of 8 in order to fulfill this equation. We can also write it like so. So we can say, now let's bring this in front and divide out by 2. So that will be the minus 1. And the square root of 8 divided by 2 will be then square root of 2. This is now the scaling we have in front of this 1 over the r squared c squared. Now we now take the square root of that situation for the, in order to go to the omega, you need to take the square root of x. That's actually shown here. Now when you now continue, you can now take the square root of this part and the square root of that part, and that is now shown here. So you will lose the squares here. And this is now the expression we can again compare with our cutoff frequency of our simple first order low pass filter. So we can say now the cutoff frequency of this buffered cascade of two first order filters is now this scaling, which is the square root of minus 1 plus the square root of 2 times the cutoff frequency of the simple first order low pass filter, which is 1 over RC. And this is then approximately here, you see that 0.64, so 0.6436. So that means our cutoff frequency of our buffered circuit, two-stage, so this will be a second order filter, will be 64.4 approximately % of the cutoff frequency we have for our simple first order low pass filter. Let's now summarize the discussion so far. So we have a first order low pass filter, RC. We have then a cascaded two first order low pass filters and a buffered version of this exactly same situation. This is the circuit for the first case, the second case, and now we have also the buffered version. Now this was a transfer function for the simple first order low pass filter. This was a transfer function for the cascade of this two low pass filters. And then you have the buffered version, and you see here the only difference here is just a 3 makes here a 2. Now the cutoff frequency here, we know that again 1 over RC in the radians per second for the simple RC low pass filter. Now going to the cascaded version, that will be then actually this much, so it's actually a value which is smaller than 1, so it was approximately 0.3742. That means the cutoff frequency of this circuit is 37% or 37.4% approximately of the cutoff frequency which you have here. So it will be then much smaller. And for this case, the cutoff frequency was given by this expression for the buffered version that was approximately 0.6436. So let's say 64.4% of the cutoff frequency of a simple first order low pass filter. Okay, let's now look at the situation in the simulations. First we start with the passive first order low pass filter, and for that we use this circuit where we have the resistor of 1 kilo ohm and the C, or the capacitor, is 10 nanofarads. Now if you now use the cutoff frequency formula, etc., but first let's look at the slope. The slope here is, as said before, is minus 20 dB per decade. You can look at it actually by looking at these labels. At 2 megahertz we see here a gain of minus 42 dB, and then 20 megahertz, so which is then 10 times larger, you see here minus 62 dB, which is indeed going down by 20 dB. Now you see here the cutoff frequency labeled, and the cutoff frequency was calculated in our case using the radians per second expression 1 over RC, and using now the frequency is hertz, we can now divide this also by 2 pi, and you have this expression. I substitute here the values for the resistor and the capacitor. You will get here 15.914 kilohertz, which is exactly as we have it. You also see that the phase at that cutoff frequency is minus 45 for this situation, and you also see that this for higher frequencies, the larger frequencies, it is approaching this minus 90 degrees for the phase. Okay, now let's now go to the simulation result for the second case, which is the cascade of two passive first order low pass filters. So this is now the situation, and this is the circuit. Again, the same two values for the resistor and capacitor, but now we again add another one. What happens here? Now you see here the slope has changed from minus 20 to minus 40. You see at 1 megahertz, I mean, which is minus 72 dB. And at 10 megahertz, which is then 10 times larger, it is then going down by 40 dB, so which is now here minus 112 dB. But you also see here the cutoff frequency, which is again, of course, calculated using this formula. Now here we have determined that here. And when you now use that here, the cutoff frequency formula, we calculate using the values we have here as 5.956 kilohertz as we have it here in the simulation. So this is indeed correct. One note here, the cutoff frequency here, at that frequency, the phase is not minus 45 degrees. It's also not minus 90 degrees, like what you might think. The minus 90 degrees, which you see here, that at that phase, the frequency is actually the cutoff frequency of the situation where you have the first order low-pass filter. So this is an interesting note here. So this is not necessarily minus 45 degrees for the two-stage passive low-pass filter. Now going to the situation where you have the buffered cascade operation, again the Bode plots. This is now the circuit. You see here again the 1 kilo ohm and the 10 nanofarads. Now we have the buffer here, and now again the same first order low-pass filter. What you see is again the slope is minus 40 dB, 2 megahertz and 20 megahertz. This is going down by 40 dB. Now the cutoff frequency was given here for the buffered case like so, and now we can now substitute also here 1 over RC, and RC we know because the resistor and the capacitors are known. So we can now also go to the FCB, which is our frequency in hertz, and now if you now substitute here the values, you get here 10.243 kilohertz as we have it here in the simulations. And again here, at that frequency, the phase is not necessarily minus 45 degrees. What you see also in the previous version where you have the cascading, it started at 0 degrees in the phase and it is approaching now minus 180 degrees. So because it is a second order, you will have 2 times the minus 90 degrees phase shift for this low pass filter. Okay, the final one we'd like to discuss is about the cascading of passive first order low pass filters in the more generic way. Now you have here the first order, second order, of course same thing, and then also now the third order. I would like to now discuss the situation what happens with the cutoff frequency. Now for the situation here where you have only simple first order low pass filter, your cutoff frequency here is approximately 15.91 kilohertz. But if you cascade that, so make it second stage, as second order, your cutoff frequency is actually moved to this red line, which is now actually the situation here. And that is now approximately 5.96 kilohertz. So you go down by this much. Now when you now go to the third order, so again the same RC cascading, you will go to this pink line, which is now approximately 3.1 kilohertz. So that means if I cascade more, fourth order or fifth order, you will actually shift your low cutoff frequency for this low pass filter to the left side. So it will be only smaller and smaller. So in order to make the cutoff frequency exactly as before, you need to use a configuration where you have the circuit such that this cutoff frequency which you have originally is not changing. And that can be done using the what we call the cell and key filters or many other configuration which we will discuss in the next videos. If you have any questions about this discussion about the low pass filters, about cascading, the buffering and the calculation for the cutoff frequencies and the transfer functions, just let me know in the comment section. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.